Hello guys, hope you're doing well. My name is Mahmoud Kiasari and welcome to the new chapter of Electrical Circuit. So at this chapter, we are going to talk about a very fascinating topic, and that is capacitor. You heard it right, folks. So right now, rather than resistors, obviously we do have another kind of components, capacitors and inductors. They're two common components, and we would like to talk about them in DC condition. Probably you are going to hear that a lot in future when we are talking about AC, but right now we would like to talk about the DC wise. The very first thing we have to know is what is a capacitor? How does it work? When we are going to connect it to the DC circuit, what would it react? And so on and so forth. So without further ado, let's talk about it. As I just mentioned, right now we're going to talk about the principle and dynamics of capacitive energy storage. It means that we are going to see that what is the principle of storage in a capacitor, because this capacitor, rather than the resistor itself, is going to be considered as the component for storing the energy. Then we would like to talk about the static properties, which is what we would like to talk about. The Q is equals to CV. We will talk about what does that mean. And then we were going to talk about the dynamic behavior. It means that about the charging and discharging. You heard that a lot. And finally, we are going to have the mathematical analysis and its application. So first thing first, what is the electrical reservoir? So a capacitor is going to be a two-terminal device that is designed to store electrical energies temporarily within an electrical field, releasing it when required. So imagine that right now you do have two plates that are going to be in parallel. And when you connect these two guys to a battery or to any other kind of source, by having the electrons inside this field, you're going to have the positive and you're going to have the negative side. That's why capacitor, unlike resistor, it's going to have the polarity. This positive and negative cause electrical field. Again, we do have a difference of potential between two fields or between two plates. So by this way, we are going to store the energy using some kind of the positive and negative force, which is going to be considered as electron, and then we are going to have the energy storage. So how we can somehow calculate or quantify this energy storage? We are going to use a formula that Q is equals to CV. What is Q? Q is something we call it as charge. This shows that how much energy we are going to store inside a capacitor. C is going to something we call as capacitance. So this is something we have it as capacity of the capacitor. Obviously, they have different capacitance. And finally, we do have the voltage between the both plates or the area of the capacitor itself. So let's have the mechanical analogy when we are talking about this one. Imagine that we are going to have something as the pressure storage. And as you can see over here, by injecting more of pressure, we are going to have a bigger of capacitors or reservoir. So it means that at this point, this analog or this some kind of pressure is considered as a voltage that is stored inside our capacitor itself. So let's talk about the architecture of a capacitor. Again, as I just mentioned, your capacitor is going to have two plates. The very first one is going to be conductive plate, positive, and another one is the conductive plate, negative. Between those two, we are going to have something that we call as dielectric material. Why we do have that? Because at this point we would like to help our system or help our capacitor or whatever that we consider as a reservoir system in order to store as many as those electrons as possible inside its field. By this way, we can make sure that my capacitor has the high capacity in order to store as much as energy as it can. So the insulating layer isn't just a spacer. As you can see, the insulator layer is considered the middle layer between those two plates. And by some kind of resisting the electric field, it allows more charge to accumulate on the plates for the same voltage, effectively boosting the tank size. So common material that we are going to use for the middle layer is just air, mica, ceramic, and paper. So again, we are using that in order to help the capacitor to store as many as electrons as it can. So the very famous formula that we do have for the capacity of capacitor is something like this, that C is going to be considered as the capacitance of capacitor is something that we do have as epsilon multiplied by A divided by D. So let's just start from the very simple part. The simple part is about the area. Obviously, when we are talking about the two plates that are connected like this, they are going to make a common area among each other. So this common area is that we know that. So A is going to be meter squared, and it means that the higher area itself, we do have the higher amount of capacitance. Then we do have the D, or the distance between two plates. So at this point, obviously, if I try to or increase the distance, I do have the less chance to have the better capacitance. So it means that decreasing the distance is going to give me a higher capacitance, and also increasing that is going to give me less amount of capacitance. And finally, we do have something we call as permeability or permittivity. So some kind of term shows how strong your material or whatever you're going to use between two plates are. So this means that the higher dielectric constant is going to have the higher capacitance. If you have the better material, for instance, any other kind of material that you can have in your mind, the mica, the paper, or the air itself, by increasing this guy, you can increase your capacitor, and it can be more powerful, or it can store more amount of energy in itself. So potential energy in the field, as we were just talking about, the capacitor is going to store the energy in electrical field. It means that one plate is going to be considered as positive part, and another plate is going to be considered as negative part. So this positive and negative are going to share some energy among each other. That's something we call it as electrostatic field storage. So where's this energy goes? It goes this way. Unlike the battery that we have, unlike the battery that uses the chemical reaction, as you guys know, inside the battery we do have some kind of chemical reaction. That's why we do have 12 volt, 20 volt, whatever. It is not our concern, but capacitor is going to store the energy electrostatically in the field between its plates. The energy remains held until the discharge paths is going to provide it. It means that by having the positive and negative, you see that we do have some arrows between the positive and negative part, which is something that we call as electrical field. So how we can quantify that? There's a simple formula. That amount of energy that's stored inside the electric field for a capacitor has a high and tight relationship between the capacitor, the capacitance of the capacitor itself, and the amount of voltage. What does it mean by voltage? Voltage means that the difference of potential between the positive part and the negative part. So guys, be very careful. The voltage of capacitor is going to be a little bit different from the voltage of your source, but in the future we would see that most of the time they are the same. So this amount of energy is going to be half of CV squared. By the way, the unit measurement for capacitance is something that we call as farad, and the voltage is going to be the unit for V itself. So energy is just energy itself, as we all know about this unit measurement. So the moment of connection, this is very important. Imagine that right now I'm at a point that I do have my source, and I do have a resistance, and then I do have the capacitor itself. So the very first thing we have to know that most of the time they are going to consider two important timing. The very first timing is the t equals to 0. It means that at this point I'm not going to have any connection with the system itself when it's before the t is equals to 0, and as soon as the t is equals to 0 or more than that, I'm going to connect my switch, or at this point the switch is going to get connected and the current is going to move through this point to my resistance and through this point. But unlike the resistance that everything is going to happen so fast and everything is constant, in capacitor situation would be a little bit different. So at the step number 1 we are going to close the switch, and step number 2, current rushes into equalize the potential. It means that at the very beginning of the point, the current is going to increase so fast. Why is that? Because as we all know, when we are talking about the amount of energy inside our capacitor, we need electrons. So electrons, in order to reach to this fact or reach to the positive and negative plates of capacitors, needs time. It means that the amount of potential or amount of voltage inside your capacitor is not going to increase fast. It's not like this. The amount of voltage inside of that one is going to increase like this. At the very beginning of the point, when you don't have any electrons on your capacitor, or at least between your capacitors, the amount of electrical field that there is 0. It means that your voltage is 0. At the beginning of the point, your capacitor is going to act as a short circuit. right? When you don't have any voltage, as you guys remember, when V equals to 0, it means that you're just having a wire. So on that point, I can assume that this capacitor doesn't exist, and it is something like that. I can find my current, I equals V divided by R. As simple as that. Nothing is happening. So at T is equals to 0, your current is going to rush to your capacitor and obviously your resistor. And after some times, the capacitor is going to have fields with opposing flow. It means that on this point, your capacitor is going to be in charge in a way that on the top is going to have positive and on the bottom is going to have the negative itself. It means that after some point, your capacitor is going to act as a guy who's fighting against your voltage source. We will talk about it more. So, and finally, in step number 4, we are going to reach to the steady state or open circuit. What does that mean? It means that at some point, when your some kind of capacitor is fully charged, the amount of voltage inside your capacitor would be as the same as the amount of voltage inside your voltage source. And at this point, imagine I do have the 10 volt over here, which is the chemical energy, and I do have a 10 volt over here, which is electrical energy. Since the amount of voltage for both of these two guys are the same, means that the current that I do have is going to follow the formula delta V divided by R, right? So delta V right now is 0, means that there's no voltage difference between this point and this point. So I don't have any current. That's why at the beginning of the point, my current is considered as a maximum current. And after some time that we will talk about it, what is it? We call it as something as tau, that I will talk about it in detail. After some point, I don't have any voltage difference, so I don't have any current. That is very important. So let's try to consider this fact. Just consider this matter from the beginning to the end. So as I just told you, at T is equals to 0, we do have the maximum current. Why is that? Because at this point, I don't have any voltage over my some kind of capacitor itself. And there is no positive negative or there is no opposing voltage. So this guy is going to just act as a short circuit. And when we don't have no kind of opposing voltage, my capacitor is going to behave as a short circuit. Then we do have another condition that we call it as what? We call it as the transient phase. It means that between the time of 0 and time of fully charged, we do have the accumulating charge. Voltage across capacitor rises, pushing back against the source. It means that by injecting more and more electrons inside the capacitor itself, my capacitor is going to have this energy inside the electrical field, but in the opposite position. It means that as soon as my voltage, by the way, the voltage of my battery source is constant, this guy is going to have more and more amount of voltage during the time. But this voltage is not friendly. This voltage is going to fight against this voltage, and that is why your current, that because of the voltage difference between 2 points, is going to reduce. It means that your current is going to decrease, not normally, but exponentially. We will talk about it in detail. And finally, we do have the steady state. Means that right now, your capacitor is fully charged, and the voltage difference between this point and this point is 0, so we don't have any current. Or we say that we do have a full charge condition, capacitor's voltage is going to be as the same as voltage of the source, but on the opposite condition, and your capacitor is going to behave as an open circuit. Why? Because no current passes through that. So if we would like to quantify this rise, if we would like to talk about this, some kind of the voltage, how actually it's going to increase, as I just told you, the voltage of capacitor follows this formula, that the V is going to be considered as the voltage of the source, or the voltage that the capacitor is going to be fully charged at the end, times 1 subtracted by E to the power of negative T over R times C. And that is the formula. So let's talk about each of these terms in detail. So the voltage is just simple. It's just connection, or is direct connection with the capacitor itself. It means that at any point when your capacitor is going to be series with whatever voltage source that it has, this guy is going to be the final voltage. For example, if your source is 10 volt, it's going to be 10, it's going to be 20. Then I do have the T itself. As I told you, if the voltage of capacitor is something that is related to time, it's like a function. And by increasing the time, the voltage is going to be more and more and more. So at some point, maybe some of you would ask, after 10 milliseconds, how much voltage do I have? By using the T as a second, by the way, you can find out that. What is R is the resistance that is connected to a capacitor, and C is just the capacitance of your capacitor. As you can see over here, if I increase my T like this, if I increase that one, this term is going to increase because I do have a negative sign. Actually, this term, e to the power negative t over rc, is going to be written as e t over rc. If I assume that r and c are going to be constant, by increasing this one, I'm increasing this term, and the total term is going to decrease. So after some point, or after something that we call as a charging time, this term is going to be something around 0. That's why the voltage of your capacitor is going to be what? Is going to be V, or the voltage of source, or whatever thing that is connected to. On another hand, we do have the currents. That means that the current is going to follow another formula. The V over R is just the famous Ohm's law, but is going to be multiplied by neg E, or the Euler. By the way, E is Euler, 2.71, and you can just consider as 2.7. By connecting directly to your capacitor, the current is going to reduce again exponentially. V is just the voltage source, R is just the resistance, and this RC we know that, and T is going to be each time. So at this point we do have two conditions, the voltage and current. And voltage describes the climb from 0 to the source voltage, and current describes the drop from the maximum current to 0. So one thing that we have to know is there is something we call as a time constant. The time constant, or tau, which we issued with this Greek letter, is R times C. What is that? The time required for the capacitor to charge exactly 63.2% of its final voltage is something that we call as tau. Maybe some of you would say that this is 63%. How much does it take for a full charge? The full charge most of the time happens as 5 tau. It means that after 5 tau, or if I consider my T as 5 tau, my voltage of capacitor is going to be somehow the same as the voltage of the source itself. So let's see the visualization. As I just told you, the capacitor voltage is going to increase like this. So the voltage of capacitor, again, VC with timing, equals to V0, or V, the source, times 1 subtracted by negative T over RC. We know RC as tau, so sometimes they call it as tau, or sometimes as RC. As you can see over here, we are dealing with exponential condition, that your V is going to decrease exponentially, and finally at the end of the day, or after 5 tau, this is considered as 1 tau, by the way. It means that right now you have 63% of your maximum voltage. So after 5 tau, you're going to have the maximum voltage. On another hand, we do have I, or I of C, equals, which since we're talking about the series condition, it is the current of resistance and the current of the source. Doesn't matter. V divided by R multiplied by E, multiplied negative T over RC. Again, this guy is going to decrease exponentially. So we talked about the fact that actually we can use the capacitor in connection with our voltage in order to store some energy inside of that. When we are talking about the stored energy, obviously we are going to use it, right? So at this point, instead of just using a voltage source, we are going to use a capacitor. Capacitor is going to act as our source. And based on the direction of some kind of a negative positive, we can say that the capacitor is going to release the stored energy, or something we know as discharging. So we do have different kind of a step. Like the charging phase, we do have discharging phase. When the source removed, it means that the external pressure is gone. The capacitor is going to act as a battery, store the charge, flows back out to equalize. And reversal means that current flows in the opposite direction compared to charging. As you can see over here, that at this point, when I do have the positive and negative, as you guys know, my capacitor is going to be positive and negative on the opposite direction. So the beginning of direction of the current was like this, but the discharging phase, or the second some kind of source, is artificial source, but right now it's considered as a source. Since right now this guy is gone, is going to be on that way. That's why your direction would change. So let's talk about the discharging phase. Let's quantify it, talk about mathematically. As you can see over here, the voltage of the capacitor is going to be V0. What is V0? V0 means that how much voltage your capacitor has at the beginning. This is your maximum voltage, times e to the power negative t over RC, which is familiar. So at this point, we say that at the very beginning of the point, or at t equals to 0, my voltage is maximum. That completely makes sense. If you consider t as 0, the whole term is going to be 1, so Vc is going to be V0. But after some point, by increasing the timing, this term is going to reduce. By reducing this term is going to reduce. That's why your voltage is going to decrease exponentially. So what would happen to current? Again, the current is going to decrease as well. So, but the direction would be different. So your current is negative. It means that, by the way, when we talk about negative, means that it is opposite direction of the charging. If the charging was, for example, clockwise, your discharging would be counterclockwise. So IT equals to negative V0, the maximum voltage, divided by R, the resistance that it was in series with, multiplied by e to the power negative t over RC, and we do have this way of visualization. As we can see at the very beginning, we had the maximum current, but in opposite direction, and finally our current is going to be 0 itself. So what about the depletion? It means that your capacitor voltage was VCT at the very beginning of the point, and we do have it at 0, and after some point we are going to energy dissipating as heat in the resistor, which is going to be obvious. And then we do have some kind of the current magnitude that we had it as V0 divided by R, and the circuit is going to be what? We do have the direction that is got reversed. This is somehow like the previous one, but instead of just considering this point, we just consider at this point because we only care about the magnitude itself. So nothing important. So the rhythm of the circuit, or tau, or how much does it take for my capacitor to get charged? As I just told you, tau means that how much does it take for my capacitor to get charged, not fully, but 63.2% of its maximum value. So obviously, after some times, I need to see that how many taus, or how many time constants, it would take for my capacitor to get charged. So 1 tau, 63, 2 tau, 86, 3 tau, 95, 4 tau, 98, and 5 tau is 99.3. That's why we say that 5 tau is time that it takes for a capacitor to get fully charged. So the larger the resistor is going to mean that we do have a more restriction, and obviously we do have a slower time of constant. When your current is going to decrease because of the fact that your R is high, we are going to have less the speed for the electrons to move through or flow through your capacitor, and obviously it takes more time to get charged. The larger capacitor means a larger tank and obviously slower time constant. That's why their tau has a tight relationship or direct relationship with R and C itself. So let's talk about the theory. Let's talk about the practice. We talked about everything. Right now, let's talk about the fact that what would happen if we do have those parameters. Imagine we do have a case that my R is 10K and my C is 100 microfarad. By the way, micro means that 10 to the power negative 6. Micro and nano means 10 to the power negative 9 are very common prefixes for farad, because when you have a capacitor of 1 farad, it's going to be huge. That's why when we are trying to talk about the practical capacitor, we do have it as micro or nanofarad. The supply voltage is 12 volts, and the question is simple: voltage at 0.5 seconds. This means, imagine that after 0.5 seconds, how much voltage do I have? Right now, I need to write down a formula. What was the formula? The formula says that the voltage of your capacitor equals to V0, or whatever some kind of supply is connected to, 12 times 1 subtracted by e to the power negative t over RC. Since R is 10 kilo ohm, we have to convert it to ohm. The 10 kilo ohm means that 10,000 ohm. On another hand, we do have 100 microfarad, 100 times 10 to the power negative 6. So the timing, or t, is going to be near negative 0.5. So if we do all of that, and if we some kind of put everything over here, we are going to reach to a number like this. What about time to 90% of the charge? What is 90% of the charge? It means that my maximum voltage was V, or 12, and my 90% is 0.9 of V. So 0.9 of V is equals to V times 1 divided by 1 subtracted by e to the power negative t divided by RC. So if you just do a couple of math or calculation, again, it's not that hard. It's something, a relationship between the exponent and ln. So you guys, I believe, know better than me. And finally, you can find your timing itself. As simple as that. So as you guys just saw, we were talking about the capacitor, a very fascinating component or charging component that we do have it in electrical circuit. We are going to see that guy a lot. Maybe not in DC, but most of the time in AC circuit. And we would see that what would change, as we just saw, the difference or the timing would matter at this point. Your voltage or current is not going to increase so fast. It's not like a resistor. It takes some time. It opposite the whole thing, and at the end of the day, whatever voltage that this guy is going to produce or whatever voltage this guy is going to store is going to fight completely against your main voltage. That's why at t is equals to 0, your capacitor is acting as a short circuit. It doesn't have any energy, it doesn't have any voltage, and after some time, after something we know as 5 tau or the full charging capacitor, we are going to have this some completely open circuit because those voltages are the same, are going to fight against each other. If you have any question, please just comment me down below. By the way, the next video, probably 99% would be about more example and questions related to capacitor, because I would like you guys to completely understand that what would happen if my capacitor is not in a series relationship, if my capacitor was a little bit different. What would happen if we do have a different capacitor side by side in parallel or in series? Probably we're going to have one at least or two more videos for you guys to make sure that completely understand anything. If you like this video, I would be more than happy to share it with others. My name is Mahmoud Kiasari. Thanks for being here with me. Have yourself a great day, night, whatever. See you around.